Welcome to the channel where we deep dive into the art of tech and gaming. And today we are exploring the iconic lighting of Far Cry 2 and Far Cry 3. In Far Cry 2, the red tinted lighting, I know most of you have played the game Far Cry 2 and you've seen the red tinted lighting. The atmosphere is usually reddish, brownish, dustish, compared to Far Cry 3 where we have a strong white lighting. So I'm going to explain to you why Far Cry 2 is that way compared to Far Cry 3. In Far Cry 2, the red-hued lighting reflects the African setting, emphasizing a gritty, oppressive atmosphere of war and justice. The warm reddish tone underscores the chaos, violence, and moral decay central to the game's narrative, evoking a sense of constant danger and unrest. In contrast, Far Cry 3 employs white, vibrant lighting to depict a tropical island where fun, touristy adventure spirals into chaos. The bright, overexposed white highlights a paradise gone wrong theme, contrasting the initial allure of the settings with the dark underbelly of its story. These lighting choices set the thematic tone but are implemented through distinct technical systems, which we'll explore below without further comparison. So I'm going to go to some technical explanations of game mechanics of Far Cry 2, and I'll break them down. In the specified mechanics for Far Cry 2 and 3, focusing primarily on Far Cry 2 for consistency, as most mechanics align with its context, using game programming, system programming, AI programming, and physics programming. I'll incorporate fundamental technical details, including quantified aspects like the ESTA algorithm for enemy AI, while keeping explanation grounded and precise.
Very soon, it's probably the last one full of rich people. Only money and connections can get you out there.
To go to player interacting with the car using a spanner to repair. When you play the game, you'll see, as you're seeing in the video, you'll see much later that there's a part where the player goes, open the vehicle's hood and repairs the engine so that the vehicle can be drivable. This is implemented by game programming, where the car repair mechanics is a scripted interaction tied to an animation state machine. When the player initiates the repair, pressing an input key like E, or some of the players use a Xbox controller or PS4 5 controllers, the game triggers a predefined animation where the character uses a spanner. This is managed by a finite state machine FSM, where the car's damaged state transitions to repairing and then repaired upon completion. The repair process might take 3 to 5 seconds, governed by a timer in the game loop. The interaction relies on the game engine's input handling system. For example, DirectX or a custom input layer processes keyboard or mouse inputs or controller inputs, mapping them to the repair action. The car's health is a float value, let's say for example 0 to 100, and repair increments, and the repair increments this value at a rate like 10 health points per second, stored in memory and updated in real time. The car physics model is likely using a rigid body system, e.g. Havoc or SciX, normally associated with NVIDIA. So it normally uses Havocs or SciX, remains static during the repair to prevent movement. The spanner collision with the car triggers particle effects, e.g. sparks, via a particle system with parameters like emission rate 10 particles per second and velocity 1 to 2 meters per second. And in such situation, when the player is repairing the vehicle, there is usually no direct AI involvement, but nearby enemies may detect the repair action sound, e.g. 20-meter radius, and trigger an investigation state to see what's happening around the vehicle. So in the video, if there were enemies around the vehicle, the sound of the spanner repairing the vehicle might trigger them and make them to attack. This is implemented by AI programming. And then you'll see before the player gets in the vehicle, he receives a phone call. The phone is a user interface element integrated into the game's HUD system, activating the phone, e.g. via a keybind like M or game controller, processes the gameplay and renders a 2D map overlaying using a user interface framework, e.g. Scaleform. The map displays textures and icons with navigation handled by a rigid-based system where each cell represents a 10 by 10 meter area. The phone map data is loaded from a database, e.g. SQLite or a custom binary format, stored on disk with coordinates serialized as X and Y pairs. Rendering is optimized using a code tree to call off screen maps section, reducing draw calls to 100 per frame. There is no physics applies directly as the phone is non-physical user interface element. There is also no direct AI programming involved in such a scene. Maybe if the sound or the light may alert enemy detection systems and trigger the enemies to start shooting at you. And then when you drive the vehicle, you're going to see that the vehicle is responding to bumpy grounds. This is implemented by physics programming. The car physics is handled by a vehicle dynamic system using a rigid body with a mass, e.g. 1000 kilograms, and a suspended model. Each wheel uses a spring damper system with a spring constant of, let's say, 50,000 newtons per meters damping coefficient and a damping coefficient of 2000 newtons per meters to respond to terrain. The terrain height maps sampled at 10 centimeters intervals dictate vertical displacements with forces applied via Newton's second law. On bumpy terrain, the car angular velocity might fluctuate by, let's say, positive or negative 5. The game engine queries the terrain collision mesh to adjust the car transform, position and rotation. Visual feedback like wheels animation synchronizes with suspension data using inverse kinematics. The physics simulation runs at a fixed time step, e.g. 60 Hz to ensure stability with data synchronized across CPU threads for rendering and physics updates. There is no AI involvement, but passengers, they may react to sudden movements via scripted events in their behavior trees. And then you'll notice that when you drive into some zones, the player health reduces and the player dies. This is implemented by game programming where closed zones are defined by trigger volumes, e.g. axis aligned bounding boxes or AABBS in the game world. When the player position enters the volume checked via a collision detection, a script triggers damage over time effects reducing health, e.g. 20 health points per second until death. A user interface warning, e.g. red flash, is triggered to accompany this. The trigger volume coordinates are stored in a special database queried each frame. The death event resets the player to a checkpoint, loading a new game state from the disk or the last saved game state from the disk, especially the last game saved state. Then there is the physics programming. In this situation, there is no physics applying unless environmental effects, e.g. radiation particles, are simulated using particle system with the randomized velocity. Enemies may patrol near the closed zone with their AI navigation constrained to avoid these areas if they were to apply AI programming in such a scenario. But here they have not applied, or the level at which I am at, there is still no AI programming applicable. And then have when I drive along this road, you are going to witness there are some trees waving, and this is mostly done by physics programming. Trees use a simplified physics model, often a skeletal animation with joints, e.g. branches driven by a wind force. The wind is modeled as a Perlin noise function, applying a force, e.g. 10 to 20 newtons, with a frequency of 0.1 to 0.5 hertz to simulate natural swaying. Vertex shaders displace foliage geometry in real time with a maximum displacement of, let's say, 0.5 meters. The animation is pre-computed and blended with real-time physics for performance, using a level of details LOD system to reduce vertex count for distance trees, e.g. less than 500 vertices at 50 meters. System programming wind data is stored in a global buffer updated at 10 Hz and shared across shaders via the GPU. There is no AI involvement in such a scene. And then you see there is also a part where you see the player is sick, especially in Far Cry 2. The player usually suffers from malaria, so the player must rest to go for missions due to sickness. And the player sickness is modeled as a status effect with a timer, e.g. 10 minutes interval. Resting triggers a scripted sequence fading the screen to black and advancing game time, e.g. 6 game hours. A health stamina stat 0 to 100 regenerates at a rate like 5 points per second during rest. System programming ensures that the sickness timer runs on a separate thread, updating a global state variable. Resting saves progress to a disk using a binary save file. There is no AI programming in such a scene or physics programming in such a scene. And then enemies can... And then when you look at the shooting scene, you will see that when I shoot at the enemies take cover and look for clear shots. Here, AI programming has been applied very heavily. Enemies use a behavior tree to manage states like patrol, alert, and cover and attack. The cover system relies on the A-star algorithm for pathfinding to cover nodes, predefined points like walls or rocks. A-star operates on a nav mesh graph of walkable polygons, e.g. 10,000 triangles with nodes spaced 1 meter apart. The cost of function of A-star is, for example, cost is equals to distance plus heuristics, e.g. Euclidean distance to target, plus cover bonus, e.g. plus 50 nodes behind the cover. Such time is usually O bracket node log node, for typically resolving in less than 1 meters per second for a 100 by 100 meters area. Enemies evaluate lines of sight using raycast, e.g. 10 rays per second to check for clear shots with a visibility threshold, e.g. 80% unobstructed. Game programming is implemented in such a scene where you see cover nodes are tagged in the level editor with attributed likes, with attributes like height 1.5 meters for crouching. The enemy's animation blend into cover stance using inverse kinematic for leaning. And nav mesh data is pre-computed and stored in memory, 10 megabytes, for example, with A-star algorithm running on a dedicated AI thread to avoid frame drops. And raycast for line of sight use the physics engine collision system, checking against the world triangle mesh. And then you'll notice that the last enemies, after I have shot all his colleagues, will run and go where the machine gun is and try to attack me with the machine gun. This is implemented heavily by AI programming. The last enemy's behavior is a scripted transition in the behavior tree, triggered when the enemy count in a squad drops to 1 and tracked via global counter. The enemy uses A* algorithm to pathfind to a predefined machine gun node with a high priority cost modifier, e.g. -100 to favor the gun. The A* algorithm recalculates the path every 0.5 seconds to adapt to player movement with a maximum path of about 50 meters. The machine gun is a static object and uses state triggering an animation, e.g. mounting the gun and enabling high damage attack, e.g. 50 DPS. A cooldown, e.g. around, let's say, 2 seconds, prevent instant use. The AI decision to rush to the gun is processed in the AI update loop with the machine gun state synchronized across networks client in a multiplayer gaming mode. The machine gun projectile use ballistic physics with a velocity of 900 meters per second and gravity applied. The mechanics above are implemented using a combination of game programming, animation state machines, system programming, input handling, data management, AI programming, e.g. A* pathfinding behavior trees, and physics programming, vehicle dynamics, and wind effects. Quantified details like A* programming, cost function, or physics parameters ground this system in fundamental technical principles, ensuring the immersive and responsible gameplay you experience in Far Cry 2. Thank you for watching this video, and expect more videos where I'll be doing technical breakdown of how these games are made.